Okay, the first task is about cross-sections. Now, the microscopic cross-section is perhaps the most fundamental thing in neutronics. This characterizes the effective size of the nucleus. The nucleus is not as big as its physical size. They appear larger or smaller to neutrons, and this microscopic cross-section tells us its effective interaction cross-section. So it's used in all the simulations, and we're going to see how it folds into the equations later on. To figure it out, it's measured experimentally with monoenergetic neutrons. So these neutrons might be fired at a target, a very pure foil, and interaction cross-sections would be measured. The X4 database, these black error bar lines, collects up the experimental data, and then evaluations like NDEF, Jeff, Jendal, and Sendel, and there's others as well. Evaluations fit these lines with different weighting factors onto the experimental data, and they come up with an integrated cross-section as a function of energy. So this reaction here is showing beryllium-9 N2N, that's one neutron in, two neutrons out, probability. It's measured in barns, and there's a whole list of different interactions. We saw neutron multiplication, but there are hundreds. So this website here has got a big list of them all. So we see NT number 1, reaction number 1 is the total interaction, quite an important one. That's a catch-all. And I'm looking for 205 because that's another important one, total tritium production. So that's useful for fusion. So this is a list of reaction numbers, and it goes up to about 1,000. We're going to use 444, which is the DPA cross-section, and 205, which is the tritium cross-section. X, capital X, is a wild card in this case. So there's four equations that come together to decide the reaction rate, and they involve the cross-section. So to begin with, there's neutron flux. This is a product of the neutron density and the neutron velocity. Another equation is number density. This is equal to the density times Avogadro's number divided by the molar mass. And then you've got the macroscopic cross-section, which is a product of the number density, which we've got here, and the microscopic cross-section. So this is, if the microscopic cross-section is the effective area of one nuclei, multiplying it by the number density gives you the effective cross-section of all the nuclei. And then your reaction rate is simply your macroscopic cross-section multiplied by your neutron flux, and that will give you your reaction rate. Remember, this microscopic cross-section is a function of energy, so you need to know the energy of the incident neutron to find out the reaction rate, as well as the density of the material, the number density of the material, and the neutron flux. Let's have a look at task 1 now. So I've got the GitHub page for the OpenMC workshop here, and I'm going to run the Docker file. Just putting in a sudo to grant admin rights. I need admin rights on my computer setup, but you might not. And I'm going to open that link. Here's my Dockerized environment, and here's the task 1. So we'll start with the first part of task 1, and this workshop is simply about plotting isotope cross-sections. So this first one just plots the neutron multiplication of beryllium-9 and lead-204, two important neutron multipliers. So we run this by pressing Shift and Enter, and we can see they have cross-sections measured in barns, and they're a function of energy. So beryllium has a lower threshold, but lead has a higher probability if you've got enough energy. We can loop through all of the lead isotopes, and create an isotope plot, and that's what that one does. And this one loops through every single isotope we've got in the nuclear data, plotting the neutron multiplication. And from this final plot, which will take a little while to plot, you should be able to see why beryllium and lead are used